What's up everyone? Today we're going to be taking a deep dive into the world of SN curves, an essential concept for anyone interested in material science, mechanical engineering, or product design. SN curves, also known as Euler curves, represent the relationship between cyclic stress amplitudes and the number of cycles to failure for a given material. Let's break that definition down. Cyclic stress amplitudes refers to the magnitude of the alternating or fluctuating stresses applied repeatedly on a material. This could be due to something like vibration, loading, unloading, temperature changes, etc. The number of cycles to failure means just how it sounds. The number of these stress cycles the material can endure before it breaks or fails. Now, you may be wondering, why do we even care about applying repeated stresses to materials until they fail? Well, the fact is that many real-world components and products experience these type of cyclic stresses throughout their lifetimes. Take airplane wings, for example. Every time the plane takes off and lands, the wings experience unloading and loading stresses. Or even something as simple as the bicycle chain is subjected to repeated stresses every time you pedal. If engineers didn't understand how materials behave under these conditions, products would start failing unexpectedly, leading to potentially disastrous consequences. This is where SN curves come into the picture. By generating SN curves for different materials, engineers can better predict how long a product will last before failure when subjected to cyclic stresses. This helps them choose the right materials and design optimized components that are safe and durable. For students and R&D professionals, studying SN curves provide great insights into how materials work and how their properties can be improved. In today's video, we will start with the basics of SN curves, then explore the various factors that influence them. We'll also learn how to actually generate SN curves for materials in the lab and discover how to properly analyze and interpret them. Finally, we'll see some real-world applications in product design and development across industries. By the end, you'll have a solid understanding of this concept. Alright, let's get started. Now that we've touched a little bit about SN curves and why they matter, let's dive into the basics. First, let's take a closer look at how these curves are graphically represented. As we mentioned earlier, the y-axis represents the cyclic stress amplitude denoted as S, while the x-axis represents the number of cycles to failure denoted as N. An important thing to note is that x-axis with the number of cycles is usually plotted on a logarithmic scale rather than linear scale. Here are the reasons why it's plotted as such. Number one is the wide range of cycles. Materials can fail after a few cycles or after millions of cycles. A semi-logarithmic scale allows for a wider range of cycles. This can be represented on the same graph without it becoming excessively wide. Number two, visual clarity. On a linear scale, the high cycle fatigue region where most engineering components operate would be compressed into a small portion of the graph. A semi-logarithmic scale spreads out this region, making it easier to interpret and analyze the data. Number three, highlighting the transitions. For some materials, especially ferrous metals, there is a transition from a steep slope to a flatter region. This transition is more evident on a semi-logarithmic scale. Number four is a tradition and convention. The use of semi-logarithmic scale for SN curves has become a standard practice in the field of fatigue analysis. Engineers and researchers are accustomed to interpreting SN curves in this format, making it easier to compare data across different studies. Number five is the analytical convenience. Some fatigue life estimation models, especially those based on statistical methods, result in equations that are linear while plotted on a semi-logarithmic scale. This linearity simplifies the analysis and prediction of fatigue life. You will notice the curve starts high in the stress amplitude axis and drops rapidly at first, then begins to level off horizontally. This curve shape demonstrates a key aspect of fatigue. Materials can typically endure higher stress values for a fewer number of cycles, but as the stress decreases, the number of cycles they can survive increases drastically. An important point on the SN curve is the endurance limit. This is the stress level below which the material can theoretically endure an infinite number of stress cycles without failing. Not all materials have a well-defined endurance limit, but for those that do, like steel alloys, knowing this value is critical for design. This is another reason that steel is a preferred material for construction. Now, there are two key parameters we can extract from the SN curve: fatigue strength and fatigue life. Fatigue strength refers to the stress level a material can endure for a specific number of cycles before failure. Fatigue life tells us just how many cycles it takes to fail at a particular stress level. For example, let's say for an aluminum alloy, the fatigue strength at 1 million cycle is 60 MPa. This means that it can withstand cyclic stress of 16 megapascal for 1 million cycles before failure. It is important to note that the shape of the SN curve can also be influenced by various factors such as surface finish, environmental condition like corrosion, temperature, residual stresses, and loading type. For example, tension, compression, which we will see in the future sections. As a result, when designing components for fatigue, it's crucial to consider the specific conditions the material will be subjected to. We'll explore all these in more detail shortly. For many materials, the SN curve can be divided into two regions, high cycle fatigue and low cycle fatigue. In the LCF region, failure occurs after a relatively low number of cycles, but at high stress amplitudes, usually considered to be below 10^4 cycles. In contrast, in the HCF region, failure occurs after a large number of cycles but at lower stress amplitudes. In the HCF region, the entire deformation is elastic, while in LCF region, the deformation is more plastic. Different materials exhibit different SN curve shapes based on their mechanical properties, microstructure, and loading conditions. Here are the typical shapes of SN curves for various materials. Number 1. For ferrous materials, example steel. These typically exhibit a knee in the SN curve. Below a certain stress level, known as the fatigue limit or endurance limit, the material can theoretically endure an infinite number of cycles without failing. This is a distinct characteristic of ferrous materials. When it comes to non-ferrous metals, they do not have a well-defined fatigue limit or a knee, so as to say, in the SN curve. Instead, the curve gradually slopes downwards, and even at high number of cycles, there is an eventual point where the material ends. The SN curve for composite materials can be complex due to anisotropic nature of these materials. The curve's shape can vary based on the fiber orientation, matrix material, and loading direction. Generally, composites may not exhibit a clear fatigue limit. When it comes to polymers, the SN curve is highly dependent on the testing temperature, loading rate, and environmental conditions. Like non-ferrous materials, polymers typically do not have a well-defined fatigue limit, and their SN curve can slope downward continuously. Also to note when testing for plastics is that they are highly frequency dependent. Since they are viscoelastic in nature, their curve can vary depending on the frequency at which you generate the SN curve. Ceramics are brittle and can be sensitive to flaws. Their SN curve can be steep and they may fail at low cycle counts when subjected to high stress amplitudes. However, some advanced ceramics designed for specific applications might exhibit better fatigue resistance. Now let's explore the various factors that can influence the shape and position of these curves. Understanding how these factors impact fatigue behavior is crucial for proper design and material selection. First, the inherent composition and microstructure of a material plays a major role in fatigue properties. For instance, if you compare different metals like steel, aluminum, titanium, each will have a distinct SN curve shape and endurance limit based on attributes like crystal structure, grain size, defects, and more. Secondly, the loading conditions experienced by a material impact its fatigue performance. The main types of cyclic loading are tension, compression, tension, or fully reversed. The stress ratio, which is the ratio of the minimum to maximum stress, also affects the curve. Higher mean stress tends to reduce the fatigue life. Typically for SN curve generation, a fully reversible load, that is R equal to -1, is used. Environmental factors like operating temperature, humidity, corrosive environments, they can significantly affect fatigue behavior. Elevated temperatures accelerate crack growth rates, moisture promotes corrosion fatigue, and chemicals can interact with compounds changing material properties. Surface finish and treatments are also very important considerations. Defects like scratches and notches act as stress concentrators, reducing fatigue resistance. Short peening and surface hardening treatments can actually induce beneficial compressive residual stresses improving fatigue performance. Other factors like loading frequency, specific geometry, sizes can all alter the ascent curve to some degree based on the material type. In summary, the ascent curve of a material depends on a variety of intrinsic and extrinsic factors. Engineers must consider all these influencing variables when designing components for optimal durability and safety. We have now covered the basics of ascent curves and the many factors that can influence them. But how are these curves actually generated in the first place? Let's go through the key steps involved in producing ascent curves from lab testing. First, you need to select a representative sample of the material you want to characterize. The geometry and the shape of the test specimen are also important considerations. Common specimen shapes include cylinders, flat dog bones, and round bars with specific dimensions. The surface finish should be consistent and smooth to avoid localized stress concentrations. Any defect could lead to premature failures. Next, you need to select the appropriate fatigue testing machine for the type of loading and frequency you want to apply. Common choices are rotating bending fatigue, axial push-pull machines, and torsional machines. The machine must be properly calibrated to provide accurate stress values. When setting up the experiment, you need to determine the stress levels you want to test and the loading conditions, like fully reversed or tension only. This is also called as R ratio that we have seen before. Typically for ascent curve generation, as we've seen, R equal to -1 is considered. It's common to start at high stress levels and gradually decrease down to near the endurance limit. The loading frequency also needs to be specified based on the material and machine capabilities. Now here's the key part. You need to test multiple specimens at each stress level, usually around 5 to 10 samples, for the results to be statistically significant. The more samples tested, the more precise the ascent curve. Here are some important statistical parameters and the recommended number of samples for the generation of ascent curves. Depending on the probability of failure and the confidence level chosen, the ascent curve is plotted as an envelope to encapsulate the range of samples meeting this criterion. A wider envelope usually means the variability is high and you will need to increase the number of samples or change your preparation. Sensors continuously monitor the stress applied and the number of cycles is counted until failure occurs. Meticulous record keeping of the test parameters is critical. The collected data must then be analyzed under statistical techniques to plot the ascent curve, usually on a logarithmic scale. Each data point corresponds to a stress amplitude and mean number of cycles to failure across all samples at that stress level. What we've also plotted is a 95% confidence interval within which 50% of the failures can occur. The more samples you take at each stress level, the confidence level increases and the probability of failure of the specimen. The plotting of the entire ascent curve would take a few weeks. If you'd like to see a more in-depth video of the generation across each stress level, let me know in the comments below. Safety is paramount as specimens can shatter violently. Protective enclosures and personal safety gear should be used. In summary, generating accurate, reliable ascent curves requires careful test planning, control procedures, rigorous statistical analysis, and safety. Now let's look at some real-world applications in product design and development across various industries. One key application is selecting materials using Goodman diagrams, which allow engineers to account for the effects of mean stress when estimating fatigue life. By overlaying operating stresses and Goodman diagrams for different materials, the best option can be chosen. In design, factors like surface finish are carefully controlled to minimize surface irregularities and defects, which can drastically reduce fatigue strength by up to even 50%. Sharp peening and surface hardening can increase fatigue life by up to 30% for certain alloys. For aircraft wings, load sequence testing provides data for fatigue analysis using Miner's cumulative damage rule. This helps determine inspection intervals to detect cracks before reaching critical size. In jet engines, thermal barrier coatings allow higher operating temperature, reducing thermal fatigue. In automotive powertrains, fatigue testing of prototypes ensure durability of components like piston rods, which undergo billions of tension compression cycles over vehicle lifetime. Suspensions are optimized using multi-axial fatigue criteria like Finlay criterion to account for combined bending and torsional stresses. For orthopedic implants, surface treatments like diffusion hardening optimize the balance between fatigue strength and wear resistance. Implants are tested in simulated body environments, accounting for effects of moisture and temperature on fatigue life. While we covered a lot in this video, there's still so much to explore about this complex topic. Before we wrap up, let's look at some common questions that users may encounter. For example, engineers wonder what the best methods are to account for variable amplitude loading in fatigue analysis. Techniques like rainflow cycle counting and linear damage accumulation models like Miner's rule provide good estimations, but more sophisticated computational methods continue to emerge. On the practical side, those working on product development often ask how to determine target safety factors when designing new components. While specific recommendations vary by industry and application, 2 to 3 times the endurance limit is a good general rule of thumb for initial design. Extensive physical testing should, however, follow. Post additional questions in the comments, and I'll try my best to respond to as many as possible. Let me know what aspects of S&curve theory or application you find most confusing or interesting. Your feedback helps guide content for future videos. If you found this overview on S&curves helpful, please like and share this video. Subscribing also allows me to keep producing more content like this. Thanks for watching. I'll see you in the next video.